There is an object in the universe so strange that it sits right at the breaking point of our understanding, a place where the rules of reality themselves seem to stop working, where space and time get so twisted that our two greatest theories of physics flatly contradict each other and neither one can tell us what is really going on. And the truly remarkable thing is that this object, for all its baffling strangeness, is in some ways the simplest thing in all of nature, describable by just a few numbers, simpler than a single atom. It is the black hole, and it is at once the most extreme, the most mysterious, and the most elegant object we know of. To understand black holes is to come right up against the edge of what human beings currently understand about the universe, and to peer over that edge into genuine mystery. So let us begin with what a black hole actually is in the simplest terms, because the basic idea is something you can grasp right away. A black hole is a region of space where gravity is so overwhelmingly strong that nothing can escape from it, not even light, the fastest thing in the universe. That is the whole definition, and it is where the name comes from, because if not even light can get out, then the object emits no light at all, and so it is quite literally black, a hole in space from which nothing returns. Everything else about black holes, all the strangeness and all the paradoxes, flows from that one simple and absolute fact that there is a place where the pull of gravity has become so extreme that escape is not difficult, but genuinely impossible, where the door only opens inward. To feel why this is so strange, it helps to think about the idea of escape velocity, which we met in the story of rockets. To leave any object's gravity behind, you have to move fast enough, and the more massive and compact the object, the faster you must go. To escape the Earth, you need to reach about 25,000 miles per hour. To escape something more massive and dense, you would need to go faster still. Now, imagine compressing matter so much, packing so much mass into so small a space, that the escape velocity at its surface climbs all the way up to the speed of light itself, around 186,000 miles per second. At that point, you would need to travel at the speed of light just to escape, and since nothing can travel faster than light, and light itself cannot escape, nothing can get out at all. That is a black hole, an object so compact that its escape velocity exceeds the speed of light, sealing it off from the rest of the universe. The boundary of a black hole, the dividing line between the region you can still escape from and the region from which there is no return, is called the event horizon. And it is one of the most profound ideas in all of physics. The event horizon is not a solid surface, not a wall you could touch, but an invisible boundary in empty space, a point of no return. Outside the event horizon, with a powerful enough rocket, you could in principle still pull away and escape. But the moment you cross that boundary, even traveling at the speed of light becomes too slow to get back out, and your fate is sealed, because there is no path, no direction, no possible motion that leads back outside, inside the event horizon. All roads lead inward toward the center as surely as outside. All roads lead forward in time. Crossing the event horizon is the most irreversible act in the universe, a one-way passage out of the observable cosmos forever. And here is something genuinely eerie about that boundary. If you watched a friend fall toward a black hole from a safe distance, you would never actually see them cross the event horizon. Because of the way gravity stretches and slows time near a black hole, which we will come to, you would see them fall slower and slower as they approached the horizon, their image growing dimmer and redder, frozen and fading at the edge, never quite seeming to cross, lingering forever at the threshold from your point of view. Yet, from your friend's own perspective, nothing special would happen at that moment, and they would sail right across the horizon and continue inward without any warning that they had passed the point of no return. Two observers, two completely different stories about the same event, both of them true. This is just the first of the many ways that black holes break our ordinary sense of how reality should behave. And to understand how we ever came to believe such bizarre objects could exist, we have to go back to the surprising history of the idea. The idea of an object so massive that light could not escape it is surprisingly old, far older than Einstein, and it first appeared more than 2 centuries ago in the mind of an English country clergyman and scientist named John Michell. In the year 1783, Michell was thinking about gravity and light, and he reasoned using the physics of Isaac Newton that if you had a star that was massive enough and compact enough, its gravity might be so strong that light itself could not escape its surface, so that the star would be completely dark, invisible from a distance. He called such hypothetical objects dark stars, and it was a remarkable leap of imagination because he had essentially conceived of the black hole in rough form nearly a century and a half before the physics existed to properly describe it. A few years later, the great French scientist Pierre-Simon Laplace independently came to the same idea, also imagining dark, invisible stars whose gravity trapped their own light. These early dark stars, however, were based on Newton's physics, which, as we learned in the story of physics, turned out to be only an approximation, and the real understanding of black holes had to wait for Einstein's theory of general relativity. Recall that in 1915, Einstein completely transformed our picture of gravity, revealing it not as a simple force, but as the bending and warping of space and time, of space-time itself by mass. In this new picture, a black hole is not just a star whose light cannot climb away, but something far stranger, a place where mass has warped space-time so extremely that it folds in on itself, creating a region from which no path leads back out. Black holes are, in a sense, the most dramatic prediction of general relativity, the places where the warping of space-time becomes absolute. What is striking is that Einstein himself did not believe black holes could really exist, considering them a mathematical curiosity rather than real objects. But within months of Einstein publishing his theory, a German physicist named Karl Schwarzschild, who was serving as a soldier on the front lines of the First World War, worked out an exact solution to Einstein's complex equations, and that solution described for the first time in proper detail what we now recognize as a black hole. At a specific distance from the center, now called the Schwarzschild radius. He did this remarkable piece of work amid the horrors of war, and tragically he died of an illness contracted at the front just months later, never living to see how profoundly important his solution would become. The mathematics of the black hole was born on the battlefield of a world war. For decades after Schwarzschild, most physicists, including Einstein, continued to regard black holes as unlikely mathematical oddities, things the equations allowed, but that nature surely would not actually produce. The turning point in taking them seriously came as physicists worked out what really happens when a massive star dies and collapses, which we will explore next, showing that the formation of black holes was not just possible, but for the heaviest stars, essentially inevitable. As the evidence and the theory mounted through the 20th century, black holes moved from the fringe of physics toward its center, transforming from a curiosity into one of the most important and most studied objects in the universe. The very name black hole, by the way, which seems so perfectly descriptive, is relatively recent, and it was popularized by the American physicist John Archibald Wheeler in the late 1960s. Before that, these objects had been called by clumsier names like collapsed stars or frozen stars, and Wheeler, who had a gift for memorable phrases, helped fix the vivid term black hole in the public and scientific imagination. The name stuck so completely that it is now almost impossible to imagine calling them anything else. A perfect two-word description of an object that is both black, emitting no light, and a hole, a place where things fall in and do not come out. With a clear idea of what black holes are and where the concept came from, we can now turn to the dramatic question of how these extraordinary objects actually come to exist in the universe, which is a story of the death of stars. Most black holes in the universe are born from the death of massive stars, and to understand how, we need to recall the great balancing act that is the life of a star, which we met in the story of astronomy. A star spends its long life in a standoff between two opposing forces. Gravity is constantly trying to crush the star inward, to collapse it under its own enormous weight, while the energy pouring out from the nuclear fusion in its core pushes outward, holding the star up against that crushing pull. For millions or billions of years, these two forces stay in balance, fusion pushing out, gravity pulling in, and the star shines steadily. But this balance depends entirely on the star having fuel to burn, and eventually every star runs out of fuel, and when it does, the outward push falters, and gravity, which never tires and never stops, finally begins to win. For a star like our sun, the ending is relatively gentle, as we saw, swelling into a red giant and then settling into a small, dense ember called a white dwarf. In a white dwarf, gravity's collapse is halted not by fusion, but by a strange quantum effect, the same exclusion principle we met in the story of physics, which makes the electrons resist being crushed too closely together, holding the dead star up at about the size of the Earth. But there is a limit to how much weight even this quantum resistance can support, a threshold of about 1.4 times the mass of the Sun. And for the cores of more massive stars, gravity overwhelms even that, crushing the matter further, forcing the electrons and protons together into neutrons, and collapsing the core into something even denser, a neutron star, a city-sized ball so dense that a spoonful would weigh as much as a mountain. But for the very heaviest stars, even the neutron star cannot hold. There is another, higher limit, and when the collapsing core is massive enough to exceed it, somewhere around 2 to 3 times the mass of the Sun, nothing in the universe can stop the collapse. No known force, no quantum effect, nothing at all is strong enough to resist gravity at that point, and the core collapses completely, catastrophically, falling in on itself without limit, crushing all that mass down toward an infinitely small point and creating a black hole. This is the birth of a stellar black hole, the final, total victory of gravity over a dying massive star, the collapse that nothing can halt. The outer layers of the star, meanwhile, are often blown off in a titanic explosion, a supernova, one of the most violent events in the universe, briefly outshining an entire galaxy, while at the center, hidden in the blast, a new black hole is born. It was the careful working out of this collapse in the 1930s by physicists, including Robert Oppenheimer, who would later lead the development of the atomic bomb that helped convince the scientific world that black holes were not just mathematical curiosities, but real physical inevitabilities. They showed that for a massive enough star, the collapse to a black hole was not merely allowed by the equations but unavoidable, that gravity, once it gains the upper hand in a sufficiently heavy star, cannot be stopped by anything we know of, and the formation of a black hole is the necessary result. This transformed black holes from a strange possibility into a predicted, expected feature of the universe, objects that the death of heavy stars must regularly produce. And produce them it does, because the universe is full of massive stars, living and dying, which means it should be full of black holes. And indeed, our galaxy alone is thought to contain many millions, perhaps 100 million of these stellar black holes, the dark remnants of heavy stars that lived fast and died young, scattered throughout the Milky Way. Most of them we cannot see because, being black, they emit no light, and a lone black hole drifting through space with nothing falling into it is essentially invisible, betraying its presence only through its gravity. There may be black holes wandering the galaxy relatively near us that we have never detected and may never find. But these stellar black holes, born from collapsing stars and typically a few to a few dozen times the mass of the Sun, are only one kind of black hole, the smaller and more common kind. The universe also contains black holes of an entirely different and far more staggering scale, monsters millions or billions of times more massive. And to appreciate how we came to take such objects seriously, we should first see how black holes went from a dismissed mathematical oddity to an accepted reality in a remarkable golden age of discovery. It is worth telling the story of how black holes went from a dismissed mathematical oddity to an accepted, predicted reality, because it is full of brilliant work and at least one painful injustice. The first crucial step came from a young Indian physicist named Subramanian Chandrasekhar, who, around the year 1930, while still just 19 years old and traveling by ship to England to study, worked out a profound limit. He calculated that a white dwarf, that dense ember left when a sun-like star dies, could only support itself against gravity up to a certain mass, around 1.4 times the mass of the sun, and that above this limit, now called the Chandrasekhar limit, nothing could stop the collapse, implying that heavier stars must collapse into something far denser and stranger. It was a deep and correct insight that pointed directly toward the existence of black holes. But when Chandrasekhar presented this result, he ran into one of the great scientists of the age, Arthur Eddington, the same Eddington whose eclipse expedition had confirmed Einstein's theory. Eddington, for reasons that were never entirely clear and may have included both scientific discomfort and less admirable motives, publicly and harshly ridiculed Chandrasekhar's work, dismissing the idea that stars could collapse so absurdly, and his great prestige effectively buried the young man's correct conclusion for years. It was a painful episode. A brilliant young scientist with the right answer publicly humiliated by an eminent elder who happened to be wrong, and it set back the acceptance of stellar collapse for a long time. Chandrasekhar was eventually completely vindicated, his limit becoming a cornerstone of astrophysics, and he received a Nobel Prize many years later. But the story stands as a sobering reminder that even in science, authority can wrongly silence truth for a time. The next great step came at the end of the 1930s, when the physicist Robert Oppenheimer, working with colleagues, took the implications seriously and calculated what would actually happen when a sufficiently massive star ran out of fuel and collapsed. They showed mathematically that for a heavy enough core, the collapse would not stop at a neutron star or anything else, but would continue without limit, the matter falling inward and the gravity becoming so strong that the object would seal itself off behind an event horizon, forming what we now call a black hole. This was the first detailed modern description of the formation of a black hole from a real collapsing star, demonstrating that these objects were not just abstract solutions to equations, but the necessary endpoint of the death of the most massive stars. And yet, remarkably, even this work was largely set aside for decades, partly because the Second World War pulled physicists like Oppenheimer into other, more urgent projects. The real revival, the period sometimes called the Golden Age of General Relativity, came in the 1960s, when a new generation of brilliant physicists returned to Einstein's theory and to black holes with fresh tools and renewed energy. A towering figure in this revival was the mathematician and physicist Roger Penrose, who in the year 1965 proved something profound, that the formation of a singularity inside a black hole is not a fluke that happens only in perfectly symmetric, idealized situations, as some had hoped, but is an inevitable, unavoidable consequence of general relativity itself, occurring in any realistic collapse. Penrose's singularity theorems showed that once collapse passes a certain point, a singularity must form, that general relativity genuinely predicts these points where it breaks down, which both established black holes as real predictions of the theory and sharply revealed the theory's own limits. For this deep work, Penrose received a share of a Nobel Prize more than half a century later. This golden age, with figures like Penrose, Stephen Hawking, John Wheeler, and others, transformed black holes from a neglected curiosity into a central and respectable subject of physics, working out their properties in detail, proving theorems about their behavior, and laying the groundwork for everything that followed, including Hawking's later discovery of black hole radiation. By the end of this period, black holes were firmly established in theory, understood to be the inevitable fate of the most massive dying stars, and a genuine prediction of our best theory of gravity, even though not a single one had yet been directly observed. The mathematics and the physics had run far ahead of the observations, confidently describing objects that no one had ever seen, in one of the great examples of theoretical prediction preceding discovery. With black holes firmly established as real features of the universe, we can survey the remarkable variety of them that the cosmos actually contains. Black holes come in a remarkable range of sizes, spanning an almost unimaginable spread of masses, and astronomers generally sort them into a few categories. The most common kind, the ones we just watched being born, are the stellar black holes formed from the collapse of individual massive stars, and these typically weigh somewhere from a few times the mass of the Sun up to a few dozen times. They are, in black hole terms, the small ones, the ordinary ones, scattered by the millions throughout every galaxy, the dark tombstones of dead heavy stars. But these stellar black holes, dramatic as they are utterly dwarfed by the other great category, the supermassive black holes, and the leap in scale between them is staggering. Supermassive black holes are monsters, weighing not a few times the mass of the Sun, but millions or even billions of times the mass of the Sun, and they sit at the centers of galaxies. As we saw in the story of the Milky Way, our own galaxy has one at its heart, weighing about 4 million times the mass of the Sun. And that is a relatively modest example, because some galaxies harbor central black holes of billions of solar masses. The supermassive black hole at the center of a nearby galaxy that we have actually photographed weighs an astonishing 6.5 billion times the mass of our Sun, a single object more massive than billions of stars combined. Nearly every large galaxy is now thought to contain one of these supermassive black holes at its core, vast dark engines anchoring the galaxies and, as we will see, deeply entwined with how galaxies themselves grow and live. One of the genuine mysteries about supermassive black holes is how they got so big, especially so early in the history of the universe. We understand fairly well how a star collapses into a stellar black hole of a few solar masses, but growing from there to millions or billions of solar masses takes either an enormous amount of swallowed matter or the merging of many black holes, and both take time. Yet, astronomers have found fully grown supermassive black holes existing surprisingly early in the universe's history, when there does not seem to have been enough time for them to grow so large by ordinary means. How these giant black holes assembled themselves so quickly in the young universe is an open and actively researched question, one of the puzzles that the newest telescopes peering back toward the early cosmos are now helping to investigate, and the answers are not yet settled. Between the stellar black holes of a few solar masses and the supermassive ones of millions, there ought, you would think, to be black holes of in-between sizes, hundreds or thousands of times the mass of the Sun, and these are called intermediate mass black holes. Curiously, for a long time, these middle-sized black holes were strangely hard to find, a kind of missing link in the black hole family, with very few solid examples known, even though it seemed they should exist as stepping stones between the small and the supermassive. In recent years, astronomers have found a growing number of good candidates helping to fill in this gap, but intermediate mass black holes remain less understood than their smaller and larger cousins, a reminder of how much we are still learning about the black hole population of the universe. There is also a hypothetical fourth category, far more speculative, called primordial black holes, which, if they exist, would have formed not from collapsing stars, but in the extreme conditions of the very early universe, in the dense moments after the Big Bang, because they would have formed in a completely different way. Primordial black holes could in principle have almost any mass, including very small ones, far smaller than any star could produce, perhaps as small as a mountain or even an atom compressed beyond imagining. Some scientists have wondered whether primordial black holes might even make up some or all of the mysterious dark matter we have discussed, which would be a tidy solution to one of the universe's great puzzles. But it is important to be clear that primordial black holes remain entirely hypothetical, never yet observed, an intriguing possibility rather than an established fact. From the wandering stellar black holes of our galaxy to the billion sun monsters at galactic cores, to these speculative relics of the beginning, the black hole family spans an extraordinary range. And to understand what they all share, we need to look closely at the anatomy of a black hole itself. For all their fearsome reputation, black holes are, structurally astonishingly simple, and their anatomy comes down to just a few features. The first and most important is the event horizon we have already met, that invisible boundary marking the point of no return, the surface beyond which nothing can escape. The size of this event horizon depends only on the mass of the black hole through a simple relationship, and the result is surprising because black holes are far smaller than people imagine. The event horizon of a black hole, with the mass of our entire sun, would be only about 6 kilometers across, small enough to fit inside a city. If you could somehow crush the Earth into a black hole, its event horizon would be about the size of a marble, a little under 2 centimeters across. Black holes are not enormous in size, they are enormous in density, taking a great deal of mass and packing it into an almost incomprehensibly small space. At the very center of a black hole, according to general relativity, lies the strangest feature of all, the singularity. This is the point toward which all the collapsing matter falls, where, the equations say, all the mass is crushed down into a single point of zero size and therefore infinite density, a place where the curvature of space-time becomes infinite and the laws of physics as we know them simply break down and stop giving sensible answers. The singularity is where our understanding ends, where general relativity, our theory of gravity, produces infinities that signal its own failure, telling us that something is deeply wrong or incomplete about our picture there. We will return to this because the singularity is one of the great unsolved problems of physics, a place where we genuinely do not know what is happening. But for now, it is enough to picture the black hole as having this impossible point at its heart, hidden forever behind the event horizon. Between the singularity at the center and the event horizon at the boundary, there is, in the simplest black holes, essentially nothing else, just empty, severely warped space. This is part of what makes black holes so strangely simple. In fact, there is a famous principle in black hole physics, sometimes playfully called the no-hair theorem, which says that a black hole can be completely described by just three numbers: its mass, its spin, and its electric charge, and nothing else. Everything else about whatever fell in, all the rich detail of the stars and gas and matter that formed it, all the complexity is lost, leaving only those three simple properties. Two black holes with the same mass, spin, and charge are utterly identical, regardless of what went into making them, whether one formed from collapsing hydrogen and the other from a fallen library of books. A black hole is perhaps the simplest object in the universe, an object that has shed nearly all information about its origins, described entirely by three numbers, which is a deeply strange and, as we will see, deeply troubling fact. Just outside the event horizon, there is one more notable feature worth mentioning, called the photon sphere, a region where gravity is so strong that light itself can be bent into a circular orbit, looping around the black hole. In principle, at the photon sphere, a beam of light could circle the black hole and come back to where it started, and if you could somehow stand there, you might see the back of your own head as light from behind you orbited around and returned to your eyes. This bending of light by a black hole's immense gravity is also what produces this strange, distorted appearance of black holes, warping the image of everything behind them. And it is part of what the famous images of black holes actually show, the glowing ring being light bent around the dark shadow of the event horizon itself. It is worth pausing on a counterintuitive point about size and density because it reveals something surprising about the supermassive black holes. While a small black hole is fantastically dense, with a lot of mass crammed into a tiny event horizon, the giant supermassive black holes are so large that their average density, the mass spread over the volume inside the event horizon, can actually be quite low, in some cases less dense than water or even air. This is because the size of the event horizon grows in direct proportion to the mass, while the volume it encloses grows much faster. So the very largest black holes enclose enormous volumes of space. For a sufficiently large supermassive black hole, you could, in principle, cross the event horizon without feeling anything dramatic at all at the moment of crossing, sailing across the point of no return without even noticing, because the gravity at that vast horizon is gentle, even though escape from within is still utterly impossible. This brings us to one of the most fascinating questions anyone can ask about a black hole, the question of what would actually happen to you if you fell into one. Imagine, then, falling into a black hole, a journey no one will ever take and return from, but one we can describe with real confidence, thanks to the physics. What happens to you depends enormously on the size of the black hole, and the difference is dramatic. For a small, stellar black hole, the experience would be gruesome long before you ever reached the event horizon because of something called tidal forces. Gravity gets stronger the closer you are to the center, and near a small black hole, the difference in gravity between your feet, which are closer, and your head, which is farther, becomes so enormous that you would be stretched out, pulled apart lengthwise, while at the same time being squeezed from the sides until you were drawn into a long, thin strand of matter. Physicists have a wonderfully grim and playful name for this, spaghettification, because you would be stretched out like a strand of spaghetti, torn apart by the difference in gravity across the length of your body, long before reaching the center. But for a supermassive black hole, the experience, at least at first, would be utterly different and far gentler, which is one of the great surprises of black hole physics. Because a supermassive black hole is so enormous, the tidal forces at its event horizon are mild, gentle enough that you could cross the event horizon entirely intact, without being torn apart, indeed, without feeling anything dramatic at all at the moment of crossing. You would sail across the point of no return smoothly, unaware that you had just passed the boundary beyond which no escape is possible, the most momentous threshold in the universe crossed without so much as a bump. Only later, as you continued inexorably inward toward the center, would the tidal forces grow and grow until they finally tore you apart as well. But the crossing of the horizon itself would be eerily peaceful, a silent passage out of the observable universe. The strangeness multiplies when you consider time because of the way a black hole's gravity warps it. To a friend, watching you fall in from a safe distance, you would never actually be seen to cross the horizon. They would see you fall more and more slowly as you approached, your image growing dimmer and shifting redder, seeming to freeze at the edge of the black hole, hanging there forever, your light stretched out and fading until it faded entirely, never quite crossing in their view. But for you, falling in, time would feel completely normal, and you would cross the horizon at a definite moment and continue inward without delay. From your perspective, you might even watch the entire future of the outside universe play out, sped up in the sky above you as you fell, the eons rushing by. Two utterly different stories of the same fall, the watcher seeing you frozen forever at the edge, you yourself crossing in an instant and racing inward, and both descriptions are correct. Each true from its own point of view. Once you cross the event horizon of a black hole, something profound happens to the geometry of space and time, something that goes beyond mere danger. Inside the horizon, the warping of space-time becomes so extreme that the direction toward the central singularity effectively becomes your future, in the same way that tomorrow is your future, unavoidable no matter what you do. Outside a black hole, you can move in any direction in space, but you cannot avoid moving forward in time toward tomorrow. Inside the event horizon, reaching the singularity becomes just as unavoidable as reaching tomorrow, a fixed feature of your future that no amount of struggling, no rocket, no effort of any kind can prevent. You cannot steer away from the center any more than you can steer away from next week. The singularity is not so much a place you fall toward as a moment in your future. You cannot escape, and this is why escape from within a black hole is not merely difficult, but genuinely, logically impossible, because escaping would be like traveling back in time. So a fall into a black hole is a one-way journey into the unknown, ending at that mysterious central point where our physics fails. For a supermassive black hole, you would cross the horizon peacefully and live for a little while longer inside, in a region from which the rest of the universe is forever cut off, before the growing tides finally destroyed you on the way to the center. And in those final moments, approaching the singularity, you would be heading into the one place in the universe where we genuinely do not know what happens, because there all our theories break down. The journey into a black hole takes you, quite literally, to the edge of human knowledge, and then beyond it into a realm we cannot yet describe. And understanding why our physics fails at that central point and what it might mean leads us to one of the deepest mysteries in all of science. At the heart of every black hole, our best theory of gravity predicts a singularity, a point of infinite density where space-time is infinitely curved, and it is worth being clear about what that really means, because it is not a triumph of the theory, but a confession of its failure. When the equations of general relativity produce an infinity, when they say the density is infinite and the curvature is infinite, physicists do not take that as a literal description of reality. Instead, they read it as a flashing warning sign that the theory has been pushed beyond its limits into a situation it cannot handle, where it breaks down and stops giving sensible answers. An infinity in physics almost always means that the theory is incomplete, that something is missing, that we have reached the edge of what our current understanding can describe. The singularity, in other words, is not really a place we understand, but a place that marks the boundary of our understanding. The reason general relativity fails at the singularity is the deep problem we met in the story of physics, the fact that our two greatest theories do not get along. General relativity, Einstein's theory of gravity and space-time, governs the very large, the realm of stars and galaxies, and the overall shape of space. Quantum mechanics governs the very small, the realm of particles and atoms. Each works beautifully in its own domain, and for almost everything in the universe, only one of them is needed at a time. But at the singularity of a black hole, you have an enormous amount of mass which calls for general relativity, crushed into an infinitesimally small space, which calls for quantum mechanics. So both theories are needed at once, and when you try to use them together, they contradict each other and produce nonsense. The center of a black hole is one of the very few places in the universe where the very large and the very small meet, and there our physics simply falls apart. What this means is genuinely humbling. We do not actually know what is at the center of a black hole. The singularity, that point of infinite density, is almost certainly not what is really there, but rather a sign that we need a deeper theory, a theory of quantum gravity that can handle both the immense gravity and the tiny scale at once, to tell us what truly happens. And we do not yet have such a theory, despite decades of effort by some of the most brilliant minds in physics, as we saw in the story of the universe, with candidates like string theory and loop quantum gravity, still works in progress. So the interior of a black hole, and especially its central point, remains one of the great frontiers of physics, a place we can fall into but cannot understand, where the answer awaits a revolution in our knowledge that has not yet come. There are intriguing hints about what a proper theory of quantum gravity might reveal there. Some physicists suspect that the singularity is not a real infinity at all, but that quantum effects, which our current theories cannot fully capture, would kick in at the center and prevent the collapse from reaching a true point of infinite density, replacing the singularity with something else, perhaps an incredibly dense but finite core, or perhaps something far stranger that we do not yet have the concepts to describe. There are even speculative ideas, which we will touch on later, that the interior of a black hole might connect to something else entirely. But all of this is at the very edge of theoretical physics, in the realm of educated guesses and unproven ideas. And the honest answer remains that the center of a black hole is one of the genuinely unknown places in the universe, hidden not just behind an event horizon we cannot see past, but behind a gap in our understanding we have not yet closed. This makes black holes a kind of natural laboratory for the deepest questions in physics, places where the universe forces our incomplete theories into direct conflict and shows us exactly where our knowledge runs out. They are, in a sense, cosmic signposts pointing toward the physics we have not yet discovered, marking the spot where a future theory of quantum gravity must do its work. Far from being merely exotic curiosities, black holes are at the very center of the effort to find a deeper, more complete understanding of reality, because whatever theory finally succeeds in describing what happens inside them will almost certainly be a profound new understanding of space, time, and matter themselves. And remarkably, the deepest insights black holes have given us so far come not from their hidden interiors at all, but from their very edges, from a startling discovery that black holes, despite everything we have said about nothing escaping them, are not entirely black after all. For decades after black holes were taken seriously, everyone assumed they were perfectly black and perfectly permanent, objects that could only ever grow as they swallowed matter, never shrink, with nothing whatsoever able to escape them. Then, in the year 1974, a young physicist named Stephen Hawking made a discovery that overturned this completely and became one of the most celebrated results in modern physics. Hawking combined the physics of black holes with quantum mechanics, applying the rules of the very small to the edge of a black hole, and he found something astonishing. Black holes, he showed, are not entirely black after all. They very slowly emit a faint glow of radiation, now called Hawking radiation in his honor, which means that black holes are not eternal, but instead very gradually lose energy and mass over time, and will eventually, given enough time, evaporate away entirely. The most inescapable objects in the universe, it turned out, are not permanent prisons, but slowly leaking ones. The mechanism behind Hawking radiation reaches into the strange quantum nature of empty space, which, as we learned, is not truly empty, but constantly seething with quantum activity, with pairs of particles flickering briefly into existence and then vanishing again. Hawking realized that right at the edge of a black hole, at the event horizon, this quantum process could be disrupted in a way that allows the black hole to radiate energy away into the surrounding space. One common, if simplified, way to picture it is that of these fleeting particle pairs born right at the horizon. One member sometimes falls into the black hole while the other escapes outward, carrying away a tiny bit of energy. And because energy and mass are equivalent, the black hole pays for this with a tiny loss of its own mass. The real explanation is more subtle and mathematical than this picture suggests. But the upshot is firm and profound, that quantum effects at the horizon cause the black hole to slowly radiate and shrink. This discovery united, for the first time, three great areas of physics that had seemed separate: gravity, quantum mechanics, and thermodynamics, the science of heat and entropy, and it revealed that black holes have a temperature and an entropy, which was deeply surprising. A black hole, it turns out, behaves in some ways like a hot object, with a definite temperature set by its mass, and it has an enormous entropy, a measure of disorder related to the area of its event horizon. This connection between black holes and thermodynamics is considered one of the most important theoretical insights of the 20th century, a profound clue about the deep nature of space, time, and information. And it is the seed from which much of modern theoretical physics, including the holographic ideas we touched on earlier, has grown. That black holes have a temperature and obey the laws of thermodynamics is a hint, we believe, about the hidden quantum structure of space-time itself. The temperature of a black hole and how fast it evaporates depends on its size, and the relationship is wonderfully counterintuitive because smaller black holes are hotter and evaporate faster, while larger black holes are colder and evaporate more slowly. The big stellar and supermassive black holes that actually exist are fantastically cold, colder than the empty space around them, so cold that their Hawking radiation is impossibly faint and slow, and they actually gain mass faster from the matter and light falling in than they lose to evaporation. For these real black holes, evaporation is so slow as to be almost meaningless on any normal timescale, taking vastly, unimaginably longer than the current age of the universe to evaporate, spans of time with so many zeros that the numbers lose all meaning. A black hole the mass of the sun would take something like 10 to the 67th power years to evaporate, a length of time so far beyond the age of the universe that comparison is pointless. But the principle is profound regardless of the timescales, because it means that black holes are not truly eternal, that even these most permanent seeming objects have a finite lifespan and will, in the unimaginably distant future, fade away. As we saw in the story of the universe, in the extreme far future, long after the last stars have died, black holes will be among the last objects remaining, and over those almost incomprehensible spans of time, they too will slowly evaporate through Hawking radiation, the largest ones last of all, until even they are gone, leaving a universe of nothing but faint, cold radiation drifting in the dark. The black holes are the final monuments of the cosmos, and even they are not forever. And in their slow evaporation lies one of the deepest and most troubling puzzles in all of physics, a paradox so profound that it has occupied the greatest minds in the field for half a century and remains, even now, not fully resolved. The discovery that black holes evaporate led directly to what may be the deepest unsolved problem in theoretical physics, the black hole information paradox, and to understand it, you need one more idea from quantum mechanics. One of the most basic principles of quantum physics is that information is never truly destroyed. The precise details of any physical system, in principle, are always preserved, so that the past is, at least in theory, always recoverable from the present, that nothing is ever completely and utterly erased from the universe. If you burn a book, it certainly seems destroyed, but in principle, quantum mechanics insists all the information about what was written in it is still there, scrambled into the smoke and ash and heat, recoverable in theory. If you could track every particle, information can be hopelessly scrambled, but it cannot be annihilated. This is a bedrock rule of quantum physics. Now, here is the paradox, and it is a genuine collision between our deepest theories. Imagine a black hole forms from some particular collection of matter, and then over the eons slowly evaporates away entirely through Hawking radiation until it is completely gone. The trouble is that Hawking radiation, as Hawking originally calculated it, appears to be utterly featureless, the same kind of bland thermal glow, regardless of what fell into the black hole, carrying no detailed information about the specific matter that formed or fell into it. Recall the no-hair idea that a black hole is described by just a few numbers, having seemingly erased all the rich detail of whatever made it. So if the black hole evaporates completely into this featureless radiation, then all the information about everything that ever fell into it appears to be gone, truly and permanently destroyed, vanished from the universe entirely. And that flatly violates the bedrock rule of quantum mechanics that information can never be destroyed. One of our two great theories must be wrong. This is the black hole information paradox, and it is not a minor technical puzzle, but a genuine crisis at the foundations of physics, because it pits general relativity and the physics of black holes directly against the bedrock principles of quantum mechanics, and they cannot both be right as stated. Either information really is destroyed in black holes, which would mean quantum mechanics, one of the most successful theories ever, is wrong or incomplete, or information somehow escapes from the black hole, which would mean our understanding of black holes and Hawking radiation is missing something crucial. Stephen Hawking himself originally argued that information was genuinely lost, that black holes really did destroy it, and he maintained this controversial position for many years, even making a famous bet about it with the physicist John Preskill. The puzzle set off decades of intense work by many of the greatest minds in physics, all trying to resolve the impossible contradiction. Most physicists came to believe that information must somehow be preserved, that it cannot truly be destroyed, and that, therefore, the information about what fell into a black hole must somehow be subtly encoded in the Hawking radiation after all, in correlations too subtle for Hawking's original calculation to capture, gradually leaking back out as the black hole evaporates. Powerful support for this view came from the holographic ideas we touched on in the story of the universe, the startling discovery that the physics inside a region of space might be completely encoded on its boundary, which suggested a way that all the information of a black hole could be stored on its horizon and released as it evaporated. In a notable development, Hawking himself eventually conceded the bet and came around to the view that information is probably preserved, though exactly how remained unclear. In recent years, there has been real and exciting progress, with new theoretical work suggesting more concretely how the information could indeed escape, gradually emerging in the radiation in a way that preserves the rules of quantum mechanics, though the details remain subtle and the full picture is still being worked out and debated. The information paradox is, in a sense, a gift because in forcing physicists to reconcile gravity with quantum mechanics in this one specific, sharply posed situation, it has become one of the most productive guides toward the deeper theory of quantum gravity that physics is searching for. It is a place where the contradiction between our theories is so sharp and so concrete that it can actually be worked on, and many believe that fully resolving it will teach us something profound about the true nature of space, time, and information. So black holes, far from being just exotic graveyards of dead stars, sit at the very cutting edge of theoretical physics, the laboratories where our deepest theories are tested to destruction. And in recent years, these once purely theoretical objects have finally become things we can actually observe in ways that would have seemed like science fiction not long ago. So far, we have mostly pictured simple, non-spinning black holes, the kind Schwarzschild first described. But real black holes in the universe almost always spin, and often spin extraordinarily fast, which adds a whole layer of fascinating strangeness. The reason black holes spin comes from the stars that form them. Stars rotate, and a deep law of physics, the conservation of angular momentum, means that when a spinning object shrinks, it spins faster, the same effect that makes a figure skater speed up when they pull in their arms. So, when a large spinning star collapses down into a black hole, an object vastly smaller than the original star, its rotation speeds up enormously, and the resulting black hole can spin at a tremendous rate, with the region just outside its event horizon whirling around at a sizable fraction of the speed of light. The mathematics of these rotating black holes is much more complex than the simple non-spinning case, and was not worked out until the early 1960s, decades after Schwarzschild, by a mathematician named Roy Kerr, whose solution describes the spinning black holes that actually populate the universe. A spinning black hole does something genuinely mind-bending to the space around it, an effect called frame dragging. Because the black hole is spinning so violently, it actually drags the very fabric of space-time around with it, like a spoon stirring honey, twisting space itself into a whirlpool around the black hole. Near a spinning black hole, this dragging becomes so strong that within a certain region, it is literally impossible to stay still, because space-time itself is being swept around so forcefully that everything is forced to rotate along with the black hole, whether it wants to or not. There is no standing your ground there, no anchoring yourself against the spin, because the ground itself, space itself, is in motion. This whirling region around a spinning black hole, where you cannot remain stationary, no matter how powerful your rocket, is called the ergosphere, and it has a remarkable property because it turns out you can actually extract energy from a spinning black hole's rotation by clever maneuvers within this region, stealing some of the black hole's spin energy. This ability to extract energy from spinning black holes is not just a theoretical curiosity, because it may power some of the most spectacular phenomena in the entire universe. Many black holes, especially the supermassive ones at the centers of galaxies, are surrounded by swirling disks of superheated matter falling in, and some of them launch enormous jets of material outward. Beams of particles fired across thousands or even millions of light years at nearly the speed of light, among the most powerful and dramatic structures in the cosmos. The leading explanation for how these tremendous jets are powered involves exactly this extraction of energy from the spin of the central black hole. With the whirling of space-time and powerful magnetic fields combining to fling matter outward at colossal energies. So, the spin of a black hole is not just an abstract property, but quite possibly the engine behind some of the brightest and most energetic objects we can see across the universe. With the rotation of these dark giants lighting up the cosmos, the spin of a black hole is, in fact, one of the only three properties a black hole has. Those three numbers from the no-hair idea: mass, spin, and electric charge. Of these, mass and spin are the ones that matter in practice, because real black holes are not expected to carry much electric charge, since the universe is electrically balanced overall, and any charge would quickly be neutralized. So, an astrophysical black hole is essentially described by just two numbers: how much it weighs and how fast it spins. And that is genuinely all there is to know about it from the outside. A stunning simplicity for such an extreme object. Measuring the spins of black holes has become an important part of studying them, telling us about how they formed and grew. Because a black hole's spin carries clues about its history, whether it grew by steadily swallowing matter from one direction or by violently merging with other black holes. Speaking of mergers, when two black holes spiral together and collide, which we now know happens across the universe, the spin plays a dramatic role, and the merging black holes briefly form a wildly distorted, vibrating object that quickly settles down into a single, larger, spinning black hole, ringing like a struck bell as it does so, an event physicists vividly call the ring down. The final black hole's mass and spin are determined by what went into the merger, with some of the total mass actually being converted into pure energy and radiated away as ripples in space-time. This brings us to perhaps the most exciting development of all, because for most of their history, black holes were objects we could only reason about theoretically, never actually observe, since they emit no light of their own. But in just the last decade or so, that has changed completely in a series of breakthroughs that have finally let us detect and even see these dark objects directly, opening a genuine golden age of black hole astronomy. The basic challenge in observing black holes is obvious because they are black, emitting no light of their own, so you cannot simply point a telescope at one and see it the way you would a star. For most of the 20th century, black holes remained purely theoretical objects the equations insisted should exist, but that no one had ever actually detected. The first way astronomers found them was indirectly by watching their effect on the matter and stars around them. When a black hole has a companion star close enough that it can pull gas off of it, that gas does not fall straight in, but spirals around the black hole first, forming a swirling, flattened disk called an accretion disk. As the gas spirals inward, it is compressed and heated to extraordinary temperatures, millions of degrees, and at those temperatures it glows fiercely, not in visible light, but in X-rays. So while you cannot see the black hole itself, you can see the brilliant X-ray glow of the superheated matter swirling around it just before it falls in, a bright signpost marking the location of something dark and massive. The first strong black hole candidate found this way back in the early 1970s was a powerful source of X-rays in the constellation Cygnus, a system where a visible star was orbiting an unseen, massive companion that was pulling gas off it and blazing in X-rays. Careful study showed the unseen object was far too massive to be a neutron star or anything else known, leaving a black hole as the only good explanation. This object became so famous that two leading physicists, Stephen Hawking and Kip Thorne, made a friendly bet about whether it really contained a black hole, with Hawking betting against it. Partly, he joked, as a kind of insurance policy, so that if black holes turned out not to exist after all his work on them, he would at least win the bet. As the evidence mounted, Hawking eventually conceded, acknowledging that the object almost certainly was a black hole. For decades, this kind of indirect detection, spotting the X-ray glow of matter falling into an unseen massive object, was the main way we found black holes. Along with watching stars orbit the invisible giant at our own galaxy's center, the work that proved the existence of the supermassive black hole there. Then, in the year 2015, came a breakthrough that opened an entirely new way of detecting black holes and won a Nobel Prize, the first direct detection of gravitational waves. As we discussed in earlier stories, when two black holes spiral together and merge, they send out ripples in the fabric of space-time itself, waves of gravity spreading outward across the universe. After a century of effort, an extraordinarily sensitive instrument finally detected these ripples directly, picking up the faint space-time tremor from two black holes that had collided more than 1 billion light-years away, the signal of their final merger. This was momentous for many reasons, but for black holes specifically, it meant that for the first time we could detect them not by any light at all, but by the gravitational waves they send out when they collide. In effect, hearing black holes rather than seeing them. Since that first detection, many more black hole mergers have been heard, revealing a whole population of black holes we could never have found any other way, and giving us a powerful new sense for studying these dark objects across the universe. And then came the most visually stunning achievement of all, because in the year 2019, astronomers did something that had seemed impossible. They took an actual picture of a black hole. Using a network of radio telescopes spread across the entire planet, linked together to act as a single instrument effectively the size of the Earth, the Event Horizon Telescope captured an image of the supermassive black hole at the center of a distant galaxy, revealing the dark circular shadow of the black hole itself, silhouetted against the glowing ring of superheated matter swirling around it. For the first time in history, humanity had a direct image of a black hole, of the very shadow cast by an event horizon, the boundary of no return made visible at last. A few years later, the same network captured an image of the black hole at the center of our own Milky Way, the one we explored in the previous story. These images, showing a dark void ringed by light, looking remarkably like what the theories had predicted, were a triumph, turning the black hole from an abstract idea into something we have genuinely photographed. Taken together, these developments, the X-ray glow of accretion disks, the orbits of stars around invisible giants, the gravitational waves of merging black holes, and the direct images of their shadows, amount to a true golden age of black hole astronomy, a span of just a few years in which black holes went from objects we could only infer to objects we can detect in multiple independent ways and even photograph directly. After more than 2 centuries from John Michel's first speculation about dark stars, and a century after the mathematics was worked out in a wartime trench, black holes have finally and decisively crossed from theory into hard observational reality. We now know beyond any reasonable doubt that black holes are real, that they are common, that they range from the mass of a few stars to billions of suns, and that they shape the universe in ways we are still discovering. And the most powerful of these new methods, the one that lets us detect black holes even when they give off no light at all, deserves a closer look of its own because it has opened a new way of sensing the universe. The detection of gravitational waves did not just confirm that black holes exist and collide. It opened an entirely new way of sensing the universe, a new kind of astronomy that has already transformed our understanding of black holes. For all of history, every bit of what we knew about the cosmos came from light in one form or another, from visible light to radio waves to X-rays. Gravitational waves are something completely different, ripples in the fabric of space-time itself rather than waves of light, and detecting them is less like seeing the universe than like hearing it, picking up the faint tremors that violent events send shuddering through space. Since that first historic detection, the instruments have steadily improved and have now picked up the signals of many dozens, indeed well over 100, black hole collisions, each one the merger of two black holes somewhere across the universe, detected purely by the space-time ripples of their final embrace. This new sense has revealed a whole hidden population of black holes that we could never have found by any other means, because these merging black holes, out in the dark depths of space, with no companion star to light them up, would have been completely invisible to traditional telescopes. By hearing their collisions, we have discovered that black hole mergers are common across the universe, and we have begun to map out the population of black holes, how massive they tend to be, how often they collide, and how they came to be paired up in the first place. And there have been genuine surprises because some of the merging black holes detected have turned out to be heavier than astronomers expected was possible from the collapse of a single ordinary star, raising puzzles about how such heavy black holes form, perhaps through earlier mergers of smaller ones or through processes we do not yet fully understand. The new gravitational wave window has, in just a few years, both confirmed our basic picture and shaken up the details. The collisions themselves are extraordinary events to contemplate, the most powerful events known since the Big Bang in terms of raw output. When two black holes merge, an enormous amount of energy is released in a fraction of a second, not as light, but as gravitational waves, with a portion of the total mass of the black holes being converted directly into the energy of these ripples in space-time. For that brief instant, a merger can radiate more power in gravitational waves than all the stars in the entire observable universe shining together, an almost unimaginable outpouring of energy, completely invisible to the eye, carried away as a violent shaking of space itself. And that energy spreads outward across the universe, growing fainter until, perhaps a billion years later, an unimaginably tiny remnant of it passes through the Earth, stretching our planet by less than the width of an atomic nucleus, just enough for our most sensitive instruments to detect. Gravitational wave astronomy has also given us powerful new tests of our theories. When two black holes merge into one, the final black hole vibrates and settles down, ringing like a struck bell in that ring down we mention. And the precise pattern of that ringing can be analyzed to test whether the merged object behaves exactly as general relativity predicts a black hole should, including testing the strange idea that a black hole is described by just its mass and spin and nothing else. So far, the black holes we have heard merging have behaved exactly as Einstein's century-old theory predicts, a remarkable confirmation of general relativity in the most extreme conditions imaginable, the violent collision of two black holes. Each detection is both a discovery of distant black holes and a fresh test of our deepest theory of gravity, passed again and again. And this new field is only just beginning. More and more sensitive detectors are being built and planned, including ambitious proposals for gravitational wave observatories in space, which would be able to detect the mergers of the giant supermassive black holes at the centers of galaxies, events far too slow and massive for current ground-based instruments to hear. As this new sense grows sharper, we expect to hear ever more of the universe's hidden black hole collisions, to map the black hole population in detail, to witness the mergers of supermassive black holes when galaxies collide, and perhaps to detect entirely unexpected things rumbling through space-time. We have, in effect, just gained a new way of perceiving the cosmos after relying on light alone for all of history, and black holes were the first thing it revealed. It is a genuinely thrilling time with the dark, once invisible objects of the universe finally announcing themselves to us through the trembling of space itself. And for all that these dark objects swallow, they turn out to be responsible for some of the brightest and most violent spectacles anywhere in the universe. It is a delicious irony that black holes, the darkest objects in the universe, are also responsible for some of the brightest, and understanding how deepens the whole picture. The key is that while a black hole itself emits no light, the matter falling into it can blaze with extraordinary brilliance in its final moments before crossing the event horizon. When gas falls toward a black hole, it almost never falls straight in because it has some sideways motion. So instead, it spirals inward, settling into a flattened, swirling disk called an accretion disk. As the gas spirals in, it rubs against itself, and friction and compression heat it to staggering temperatures, often millions of degrees, until it glows fiercely, pouring out enormous amounts of light and especially high energy radiation like X-rays. So, a feeding black hole is surrounded by a brilliant, searing disk of doomed matter, lit up by the very process of falling in. What makes this so powerful is that falling into a black hole is an astonishingly efficient way to release energy, far more efficient than the nuclear fusion that powers stars. As matter falls deeper into the black hole's intense gravity, it can convert a large fraction of its mass directly into energy, radiated away as light before the matter finally disappears across the horizon. This is why feeding black holes can outshine entire galaxies, as we noted with quasars, producing more light from a region the size of a solar system than hundreds of billions of stars produce across a whole galaxy. The brightest sustained sources of light in the entire universe are not stars at all, but matter screaming as it falls into supermassive black holes, a profound and beautiful paradox that the darkest objects power the brightest beacons. Many feeding black holes also produce another spectacular feature: enormous jets of material blasted outward from near the black hole, beams of particles fired into space at very nearly the speed of light, sometimes stretching across distances far larger than the entire galaxy. These jets are among the most powerful and dramatic structures in the cosmos, and exactly how they are launched is still being worked out, but the leading explanation involves the intense magnetic fields threading the accretion disk, combined with the energy of the spinning black hole itself, flinging matter outward along the black hole's spin axis in tight, focused beams. When one of these jets happens to point directly at us, the object appears especially brilliant and variable, and these are among the most extreme objects astronomers study. So black holes do not merely swallow matter, they also fling enormous fountains of it back out into space, reshaping the galaxies and even the larger structures around them with their tremendous outflows of energy. There is a particularly dramatic kind of event that occurs when a star, rather than a cloud of gas, wanders too close to a black hole, and it is called a tidal disruption event. If a star strays within a certain distance, the black hole's tidal forces, that same stretching effect, that would spaghettify a falling person become strong enough to tear the entire star apart, ripping it into a long stream of stellar debris. Some of that shredded star then falls into the black hole, briefly forming a hot accretion disk and producing a bright flare of light that can outshine the galaxy for weeks or months before fading. Astronomers have actually observed a number of these tidal disruption events, watching distant galaxies suddenly brighten as a black hole devours an unlucky star, a real and observable instance of a black hole tearing a star to pieces and feeding on its remains. These flares are not only spectacular, but useful because they light up otherwise quiet black holes, revealing their presence and letting us study black holes that would normally be invisible. All of these phenomena, the blazing accretion disks, the brilliant quasars, the colossal jets, the dramatic tidal disruption flares, mean that black holes, for all their darkness, are among the most energetic and influential objects in the universe, active players that light up the cosmos and shape the galaxies around them. They are not merely passive cosmic drains, but dynamic engines, converting the gravitational energy of infalling matter into some of the most powerful outpourings of light and energy that exist. The study of how black holes feed, shine, and blast out jets is a rich and active field, connecting the physics of the event horizon to the visible drama of galaxies across the universe. And these dramatic outpourings reach their greatest power around the supermassive black holes at the centers of galaxies, where the bond between a black hole and the galaxy around it turns out to run remarkably deep. One of the most surprising discoveries about supermassive black holes is that they are not just passive passengers sitting at the centers of galaxies, but are deeply and intimately connected to the galaxies themselves, growing and evolving together with them in ways we are still working to understand. Astronomers found a remarkable relationship that the mass of the supermassive black hole at a galaxy's center is closely tied to the properties of the galaxy around it, in particular to how fast the stars in the galaxy's central bulge are moving. Bigger galaxies with faster moving central stars tend to have proportionally bigger central black holes, and the relationship is surprisingly tight and consistent across a huge range of galaxies. This was unexpected because the central black hole, for all its mass, is tiny compared to the whole galaxy, and its direct gravitational influence reaches only a small region near the center. So there is no obvious reason its mass should be so precisely linked to the galaxy as a whole. The tightness of this connection strongly suggests that galaxies and their central black holes grow up together, their fates intertwined. When a supermassive black hole is actively feeding, gorging on large amounts of gas falling into it, the result is one of the most spectacular phenomena in the universe, an object called a quasar, which we met in the story of astronomy. The matter spiraling into the black hole forms an accretion disk heated to such ferocious temperatures that it blazes with the light of hundreds of galaxies, all pouring out from a region not much larger than our solar system, making quasars among the most luminous objects in the entire cosmos, visible across nearly the whole observable universe. So, a feeding supermassive black hole, far from being dark, can light up the heart of its galaxy more brightly than all the galaxy's stars combined. A brilliant beacon powered by matter in its final moments before crossing the event horizon. The most distant quasars we can see are powered by supermassive black holes that existed in the early universe, and they are among the farthest and oldest objects we can observe. The energy a feeding black hole pours out also affects its host galaxy profoundly in a process astronomers call feedback. The intense radiation and the powerful jets launched by an active supermassive black hole can heat up and blow away the gas in the surrounding galaxy, the very gas that the galaxy needs to form new stars. So, a black hole, by violently feeding, can actually shut down or slow the formation of new stars in its galaxy, regulating the galaxy's growth, acting almost like a thermostat that prevents the galaxy from forming stars too quickly. This is now thought to be a crucial part of how galaxies evolve, with the central black hole and the galaxy locked in a kind of feedback loop, the black hole's activity shaping the galaxy and the galaxy's gas feeding the black hole. It helps explain that tight relationship between black hole mass and galaxy properties, because the two are not growing independently, but are influencing each other, evolving together over cosmic time. This deep connection has changed how astronomers think about galaxies entirely, because it means you cannot fully understand a galaxy without understanding the supermassive black hole at its heart, and you cannot understand the black hole without understanding its galaxy. The dark engine at the center is not a separate thing from the galaxy, but a central organ that shapes and is shaped by the whole, woven into the galaxy's life story from the beginning. Our own Milky Way central black hole is relatively quiet now, not actively feeding much, but it likely had more active phases in the past, and those past eruptions, like the great bubbles of gas we found extending above and below the galactic center, are evidence of times when our galaxy's central black hole was far more active and far more influential on its surroundings. There remains the deep mystery we touched on earlier of how these supermassive black holes grew so enormous so quickly in the early universe, because the newest telescopes keep finding fully grown giants surprisingly soon after the Big Bang, when there hardly seems to have been time for them to assemble such mass by ordinary feeding. This puzzle is driving active research, with ideas ranging from black holes that started out unusually large, perhaps from the direct collapse of huge gas clouds rather than from individual stars, to periods of extraordinarily rapid feeding, but the question is far from settled. It is one of the frontiers where black hole physics and the study of the early universe meet, and where the newest observations are actively reshaping our understanding. Black holes, in other words, are not just exotic endpoints, but central players in the grand story of how the universe came to look the way it does, woven into the formation and evolution of the galaxies that fill the cosmos. And beyond even these connections lie some of the wildest and most speculative ideas in all of physics, ideas about what black holes might ultimately be and what they might connect to. Black holes sit at the edge of known physics and so they naturally attract some of the wildest and most speculative ideas in science, possibilities that are allowed by our equations, but that we cannot confirm and may never be able to. The most famous of these is the wormhole. It turns out that the mathematics of general relativity allows, at least on paper, for solutions in which a black hole connects to another region of spacetime, forming a kind of tunnel or bridge between two distant places in the universe, or even between two different universes. These hypothetical tunnels, sometimes called Einstein-Rosen bridges, have captured the imagination as possible shortcuts across vast distances, the stuff of countless science fiction stories. But it is important to be clear-eyed about them, because the wormholes that emerge naturally from the equations are not passable, collapsing too quickly for anything to travel through, and crushing anything that tried. To hold the wormhole open long enough to travel through would require exotic forms of matter with strange properties that we have never observed and that may not exist at all. So, while wormholes are a genuine feature of the mathematics, the idea of using them to travel across the universe remains firmly in the realm of speculation, a tantalizing possibility with no evidence that nature actually provides them. A related idea from the equations is the white hole, which is, in a sense, the time reverse of a black hole, where a black hole is a region that things can only fall into and never leave. A white hole would be a region that things can only come out of and never enter, spewing matter and light outward while nothing can fall in. White holes are perfectly valid solutions of the equations, just as black holes are. But unlike black holes, there is no known way for them to actually form in our universe, and most physicists believe they do not really exist, that they are mathematical possibilities that nature does not realize. Still, the idea is intriguing, and some highly speculative theories have wondered whether the matter that falls into a black hole might somehow emerge from a white hole elsewhere, or whether the Big Bang itself, that great outpouring of everything from a single point, might have something in common with a white hole. These remain fringe ideas, far from established, but they show how black holes push us to think about the deepest structure of space and time. The most profound idea to emerge from the study of black holes, though, is not about travel or exotic objects, but about the very nature of reality. And it is the holographic principle we met in the story of the universe. Recall that the study of black hole entropy revealed something deeply strange, that the amount of information a black hole can contain depends not on its volume, as you would expect, but on the area of its event horizon, on its surface rather than its interior. This startling fact led physicists to a radical conjecture that perhaps all the information about what is inside any region of space, including all the three-dimensional richness within it, can be completely encoded on its two-dimensional boundary like a hologram, and that our entire three-dimensional reality might, in some deep mathematical sense, be a projection of information stored on a distant surface. Black holes, in other words, may have handed us one of the most important clues we have about the ultimate nature of space, time, and reality itself. A clue that the solid three-dimensional world we inhabit might not be as basic as it seems. This idea, born from thinking about black holes, has become one of the most active and promising areas in all of theoretical physics. It is worth stepping back to appreciate just how central black holes have become to the search for a deeper understanding of the universe. They are the places where our two greatest theories collide and where their contradiction is sharpest, at the singularity and in the information paradox, making them the natural testing ground for any future theory of quantum gravity. They have revealed the deep and unexpected links between gravity, quantum mechanics, and thermodynamics through Hawking radiation and black hole entropy. They have given us the holographic principle and its hint that reality may be, at bottom, about information, and they have become, through gravitational waves and direct imaging, real objects we can study observationally with ever increasing precision. Far from being mere cosmic curiosities, black holes have moved to the very center of theoretical physics, the place where many believe the next great revolution in our understanding will be found, the keyhole through which we are trying to glimpse the deeper laws of nature, and black holes will, in the end, outlast almost everything else in the universe. As we saw in the story of the cosmos, in the unimaginably distant future, long after the last stars have burned out and faded, the universe will enter an era dominated by black holes, the last great structures remaining in an ever-darkening cosmos, slowly drifting and occasionally merging in the cold and the dark. And then, over spans of time so vast they defy all comprehension, even the black holes will slowly evaporate through Hawking radiation, the smallest first and the largest last, until the very final black hole winks out, leaving a universe of nothing but the faintest, coldest radiation, spread impossibly thin. Black holes are, in a real sense, both the most extreme objects of the universe produces and its final monuments, the last things to go. But before we draw all these threads together, it is worth pausing to clear up some of the common fears and misconceptions about black holes, because the truth is both less frightening and stranger than the popular image. Black holes inspire a lot of fear and confusion, much of it understandable but mistaken, so it is worth gently clearing up some of the most common misconceptions, because the reality is far less alarming than the popular image suggests. The biggest misconception is that black holes are cosmic vacuum cleaners, roaming the universe, sucking everything into them with some special, irresistible pull. This is simply not true. A black hole's gravity is no different at a given distance from the gravity of any other object of the same mass. The pull of a black hole is only extreme when you get very close to it, near its tiny event horizon, but from a distance, it pulls exactly as a normal star of the same mass would. Black holes do not reach out and grab things from afar. They simply have ordinary gravity that becomes overwhelming only in the small region right around them. The clearest way to feel this is with a thought experiment. If you could magically replace our sun with a black hole of exactly the same mass, which cannot actually happen, but if you could, the Earth and all the other planets would continue orbiting in exactly the same paths as before, completely undisturbed, because the gravity at our distance would be unchanged. We would not be sucked in. The only difference would be that the sky would go dark and cold because the black hole would give off no light or heat, but gravitationally nothing would change at all, and the Earth would keep circling peacefully where it always has. The planets are in no danger of being swallowed by a black hole simply appearing in the sun's place, because a black hole is not a magic drain, just a very compact mass with the same gravity as the mass it is made from. Are we, then, in any danger from real black holes? The reassuring answer is no, not in any practical sense. The nearest known black holes to Earth are well over 1,000 light years away, an enormous distance, and none of them are headed toward us, so they pose no threat whatsoever to our solar system. Now, or for any foreseeable future, black holes do not go hunting for planets, and the vast emptiness of space means that close encounters are extraordinarily rare. The supermassive black hole at the center of our galaxy, despite its size, is tens of thousands of light years away and holds us in a stable orbit, no more a danger to us than the sun is a danger to the earth. You can rest entirely easy on the question of black holes, which are, for all their drama, a very distant concern. There was also, some years ago, a wave of public worry that a powerful particle collider here on Earth might accidentally create a tiny black hole that could grow and swallow the planet, a fear that, while understandable, was entirely unfounded, and it is worth explaining why. First, even if such a collider could produce a microscopic black hole, which is itself highly uncertain, that tiny black hole would, according to Hawking's work, evaporate almost instantly in a tiny fraction of a second, long before it could swallow anything at all. And second, and even more reassuringly, nature has been running this experiment for billions of years already, because cosmic rays, particles from space, strike the Earth's atmosphere and the surface of the moon and other bodies constantly with energies far higher than any collider can produce, and have done so for the entire history of the solar system without ever creating a dangerous black hole. If it were possible to make a planet-eating black hole this way, the Earth and Moon would have been destroyed long ago by natural cosmic rays. The fear, however dramatic, simply does not hold up. So black holes, properly understood, are not the menacing predators of science fiction, lurking to swallow worlds, but distant, mostly quiet objects, obeying the same laws of gravity as everything else, dangerous only if you get extraordinarily close, which nothing in our neighborhood is at any risk of doing. They are objects of wonder rather than threat, at least from our safe vantage point far away. This is worth keeping in mind, because the genuine strangeness and fascination of black holes lies not in any danger they pose to us, but in what they reveal about the deepest workings of the universe, in the way they break our physics and challenge our understanding. And on that front, Black holes have one more profound puzzle to offer, a paradox even sharper than the information problem that brings the conflict between our theories to its most acute and bewildering point. Right at the edge of the event horizon itself, the information paradox has a sharper, even more disturbing cousin discovered more recently, called the firewall paradox, and it brings the conflict between our theories to an almost unbearable point. Right at the edge of the event horizon, recall two things we have established. First, general relativity insists that crossing the event horizon of a large black hole should be completely uneventful, with nothing special happening at the boundary. An infalling observer sailing across without even noticing, because the horizon is just a location in empty space, not a physical surface. And second, the resolution of the information paradox seems to require that information escapes the black hole encoded in the outgoing Hawking radiation in a particular subtle way. Around the year 2012, physicists realized that these two requirements may flatly contradict each other, that you might not be able to have both at once. The argument is subtle, but the upshot is shocking. When physicists tried to work out in detail how information could be preserved and carried out in the Hawking radiation, the mathematics seemed to demand that the event horizon could not be the smooth, empty, unremarkable boundary that general relativity promises. Instead, it suggested that the horizon might be a wall of intensely energetic particles, a literal firewall that would instantly incinerate anything falling in, destroying the infalling observer the moment they reached the horizon rather than letting them cross peacefully. This is a direct, head-on contradiction. General relativity says the crossing is gentle and uneventful. The requirements of quantum information seem to say the crossing is fatal, a wall of fire. Both cannot be true, and which one is wrong cuts right to the foundations of physics. So, the firewall paradox forces an agonizing choice between cherished principles. Perhaps general relativity's central idea that there is nothing locally special about falling freely through a horizon breaks down, and there really is a firewall, which would be a stunning failure of Einstein's theory in exactly the place it was thought to be safe, or perhaps the rules of quantum mechanics must bend instead. Or perhaps the resolution lies in some subtler idea, like the notion of complementarity, which suggests that the description of things falling in and the description of things staying outside are both valid but can never be combined or checked against each other by any single observer, so that the apparent contradiction never actually manifests for anyone. The debate over the firewall has been fierce and is not fully settled, though recent theoretical work, drawing again on holographic ideas and on subtle features of the mathematics, has suggested possible ways out that preserve both a smooth horizon and the escape of information. But the very existence of the paradox shows just how profoundly black holes strain our deepest theories, how the simple question of what happens when you cross a horizon leads straight into unresolved foundational crisis. It is in this spirit of black holes pushing physics to its limits that some of the most speculative ideas of all arise, including the strange possibility, which we touched on earlier, that our own universe might itself be the interior of a black hole sitting in some larger reality. The reasoning is loose and unproven, drawing on certain mathematical resemblances between the inside of a black hole and an expanding universe, but it captures how black holes invite us to question the most basic assumptions about the nature of reality, even the assumption that our universe is the whole of things rather than the inside of something else. Whether or not such wild ideas turn out to have any truth, they show how black holes serve as a kind of conceptual frontier, a place where physicists are forced to think the most radical thoughts, because the ordinary picture so clearly fails there. What all of this reveals is that black holes are, more than any other object, the keyhole through which physics is trying to glimpse its own future. Every deep puzzle they present, the singularity where our theories break down, the information paradox, the firewall, the connection between gravity and quantum mechanics and thermodynamics, all point toward the same missing piece, a theory of quantum gravity that would unite our understanding of the very large and the very small, the theory we explored in the story of the universe and have not yet found. Many physicists believe that whoever finally cracks the mysteries of black holes will, in doing so, discover that deeper theory, that the road to the next great revolution in physics runs directly through the event horizon. Black holes are not just objects in the universe. They are the testing ground where our understanding of reality is pushed to its breaking point, and where the clues to its repair are most likely to be found. And that, in the end, is what makes them so endlessly worth contemplating, which brings us back to where we began, to the strangest and most revealing objects in all of existence. So let us gather up the whole strange story of black holes, these objects that began as a country clergyman's idle speculation about dark stars and ended up at the very frontier of human knowledge. A black hole, at its simplest, is a region where gravity has become so overwhelming that nothing, not even light, can escape, bounded by an event horizon that is the ultimate point of no return. They form when the heaviest stars die and collapse without anything to stop them, and they range from a few times the mass of the sun to the billion sun monsters that anchor the centers of galaxies. They are, structurally, the simplest objects in the universe, describable by just their mass and spin, having shed nearly all other information, and yet they are the most baffling, hiding at their centers a singularity where our deepest theories break down and confess their incompleteness. We have learned that black holes are not even truly black, that quantum effects make them slowly glow and evaporate over almost incomprehensible spans of time, a discovery that united gravity, quantum mechanics, and thermodynamics, and revealed that black holes have a temperature and an entropy. We have seen how that same evaporation leads to the profound information paradox, the sharp collision between general relativity and quantum mechanics that has occupied physicists for half a century and continues to drive the search for a deeper theory. We have watched black holes go, in just the last decade, from purely theoretical objects to things we can hear through gravitational waves and even photograph directly, capturing the shadow of an event horizon for the first time in human history. And we have seen how deeply they are woven into the universe, shaping galaxies, powering the brightest beacons in the cosmos, and standing as the final monuments that will outlast the stars. Let us indulge in one of the most fascinating thought experiments in all of physics and imagine carefully and accurately what would actually happen if you fell into a black hole, because the answer is far stranger and more interesting than you might expect, and it reveals some of the deepest truths about these objects. Suppose you are falling feet first toward a black hole. As you fall, you are pulled by its gravity, faster and faster. But here is the first surprise, which is that the experience depends enormously on the size of the black hole. For a small black hole, one only a few times the mass of the sun, you would be in terrible trouble long before you reached it, because gravity pulls harder on the parts of you that are closer, so your feet would be pulled much more strongly than your head, stretching you out, and the difference would grow so extreme that you would be drawn into a long, thin stream, a fate that physicists have given the wonderfully grim name of spaghettification. But for an enormous black hole, one of the supermassive giants at the centers of galaxies, the experience near the boundary would be utterly different and, at least at first, surprisingly gentle, because such a black hole is so large, the difference in pull between your head and your feet at the boundary would be small, and you could, in principle, cross the point of no return, the event horizon, without feeling anything dramatic at all, with no barrier, no wall, no sensation to mark the moment you pass the threshold beyond which return is impossible. This is one of the strangest features of a black hole, that the event horizon is not a physical surface, but simply a boundary in space, the line beyond which escape becomes impossible, and you could drift across it for a large enough black hole without noticing anything special, even though you had just sealed your fate forever, doomed to fall inward with no possibility of return. The view as you fell would be extraordinary, because the black hole's gravity bends light in dramatic ways, distorting the appearance of everything around you, and the sky behind you would be warped and concentrated as you fell, the whole universe appearing to crowd into a shrinking window above you. But the truly mind-bending part concerns time, and here the black hole reveals the strangeness of relativity in its purest form. To you, falling in, time would feel completely normal, and you would cross the horizon and fall toward the center in a finite and rather short time by your own clock. But to someone watching you from a safe distance far away, something completely different would appear to happen, because the extreme warping of time near the black hole would make your fall appear to slow down as you approach the horizon, your image growing dimmer and redder until, from their point of view, you seem to freeze at the boundary, hanging there forever, never quite crossing, slowly fading from sight. So there are two completely different but equally valid stories of your fall, depending on who is telling it. And this is not a trick or an illusion, but a deep truth about how time itself behaves near a black hole. From your own point of view, you fall straight in, crossing the horizon in moments and reaching the center quickly. From the distant observer's point of view, you never cross at all, but slow, redden, dim, and freeze at the horizon, your final image lingering there, fading toward invisibility, but never quite vanishing. Both are true because time runs at different rates in the two places, dramatically warped by the black hole's gravity, and there is no single universal answer to the question of when or even whether you crossed the horizon, which is one of the most profound illustrations of how relativity shatters our everyday notions of a single, shared, universal time. Once across the horizon, your fate is sealed, and the physics tells us something genuinely strange about what the inside is like. Within the event horizon, the pull toward the center becomes so overwhelming that moving toward the central point is no longer a choice, but an inevitability, as unavoidable as the forward march of time itself, with every possible path leading inward, so that falling toward the center becomes as certain as tomorrow following today. And at the center waits the singularity, the point where our physics breaks down completely, and where, as far as our current theories can tell, you and everything else that ever fell in would be crushed into a region of infinite density, though the truth is that we do not really know what happens there, because describing the singularity would require the theory of quantum gravity we do not yet possess. The honest answer to what would happen in your final moments at the heart of a black hole is that we genuinely do not know, that it lies beyond the edge of known physics, which is a fittingly humbling note on which to end the strangest journey one could ever take, the one-way fall into a black hole from which not even light, and certainly not you, could ever return to tell the tale. A natural question about black holes is how we can possibly study something that, by its very nature, emits no light and cannot be seen, and the answer is a wonderful story of cosmic detective work. Because, although a black hole itself is invisible, it betrays its presence in several dramatic ways, and astronomers have become expert at reading these clues. The first and oldest method is to watch how a black hole affects the matter and the objects around it, because while the black hole gives off no light, the material falling into it most certainly does. When a black hole has a companion star close enough that it can pull gas away from it, that gas does not fall straight in but spirals inward, forming a swirling disk that grows fantastically hot from friction as it is compressed and accelerated, heating up until it glows fiercely in high energy light, in X-rays before the gas finally crosses the horizon and vanishes. So, astronomers look for sources of intense X-rays that flicker and behave just as the superheated gas around a black hole should. And this is exactly how the first strong black hole candidate was found, a powerful X-ray source where a visible star appeared to be orbiting something massive and unseen. A second method, which we explored in the story of our galaxy, is to watch the orbits of stars and gas around an invisible object and use their motion to weigh whatever they are circling. If you see stars or gas whirling around an apparently empty point at tremendous speeds, you can calculate how much mass must be there to hold them in such fast orbits. And if that mass turns out to be enormous and packed into a tiny region, the only thing it can be is a black hole. This is how the supermassive black hole at the center of our own galaxy was confirmed by tracking stars whipping around the unseen center, and it has been used to find and weigh the giant black holes at the hearts of many galaxies, the invisible monsters revealed by the dance of the visible objects around them. The most revolutionary new method and one of the great triumphs of modern physics is the detection of gravitational waves, the ripples in spacetime that we have met before, which has given us an entirely new way to sense black holes, one that does not rely on light at all. When two black holes spiral together and merge, an event of unimaginable violence, they shake the very fabric of spacetime, sending out ripples that spread across the universe. And in a landmark achievement, instruments of staggering sensitivity detected these ripples for the first time, picking up the faint tremor of two black holes merging far across the cosmos. This was historic for many reasons, not least because it was the first direct detection of black holes through something other than their effect on surrounding matter, a direct sensing of the black holes themselves through the space-time ripples of their collision, and it opened a completely new window on the universe, allowing us to hear, in effect, the violent mergers of black holes that give off no light whatsoever. And then, in the achievement we discussed in the story of the galaxy, came the most direct evidence of all, an actual image of a black hole, or rather, of its silhouette against the glowing material swirling around it. By linking radio telescopes across the entire Earth into a single planet-sized instrument, astronomers captured a picture showing the dark shadow of a black hole ringed by a glowing circle of light from the superheated gas around it. First, for the giant black hole at the center of a distant galaxy, and later for the one at the center of our own. Seeing that dark silhouette, exactly the size and shape that the theory of black holes predicted, was a stunning confirmation that these objects, born as mathematical curiosities in equations, are absolutely real, that there truly are regions of space from which not even light can escape, casting their shadows against the glow of the doomed matter spiraling in around them. Taken together, these methods have transformed black holes from theoretical possibilities, which even Einstein doubted were real, into thoroughly confirmed and intensely studied objects, detected by their X-rays, weighed by the orbits of stars, sensed through the ripples of their collisions, and finally photographed in silhouette. We now know that black holes are not rare exotic oddities, but a common and important part of the universe, with stellar black holes scattered throughout every galaxy and supermassive ones anchoring nearly every galactic center, and we study them across the full range of our cosmic senses. It is a remarkable thing that we can learn so much about objects that are by definition invisible and from which nothing can escape, and the ingenuity required to detect and measure the undetectable. To study the very embodiment of darkness is one of the great achievements of modern science, turning what once seemed an untestable speculation into one of the most active and exciting fields in all of astronomy and physics. The supermassive black holes at the centers of galaxies deserve special attention because they are not just bigger versions of the stellar black holes formed when stars die, but a different kind of giant whose origin, growth, and influence pose some of the most fascinating questions in astrophysics. These monsters have masses ranging from millions to billions of times that of the Sun, and one of the deepest puzzles about them is simply how they got so big, because there has not been enough time since the beginning of the universe for them to have grown so enormous by the slow swallowing of stars and gas alone, especially the giant black holes we see in the very early universe, which were already huge when the cosmos was young. How these supermassive black holes formed and grew so quickly is a genuine open question, with astronomers proposing various ideas, from the rapid collapse of huge gas clouds in the early universe to the merging of many smaller black holes and the discovery by our newest telescopes of surprisingly large black holes very early in cosmic history has only deepened the mystery. When a supermassive black hole is actively feeding, drawing in large amounts of gas, it becomes one of the most spectacular and luminous objects in the entire universe, in a way that seems almost paradoxical for an object famous for trapping light. The trick is that the light comes not from the black hole itself, but from the matter around it, because the gas spiraling in forms a disk that grows so hot and radiates so fiercely that it can outshine an entire galaxy of hundreds of billions of stars blazing across the universe from the immediate surroundings of the black hole just before the matter disappears forever. These brilliant, feeding supermassive black holes in the early universe are what we call quasars, the most luminous, steady objects known, so bright that we can see them across almost the whole observable universe. Beacons that are really the death cries of matter being devoured by a giant black hole, and for a long time their nature was a complete mystery, their enormous brightness from such a small region baffling astronomers until the role of the central black hole was understood. Many feeding supermassive black holes also produce another astonishing phenomenon: enormous jets of material blasted outward at nearly the speed of light, shooting from the regions just outside the black hole, far out into space, sometimes extending beyond the entire galaxy. Exactly how these jets are launched is still not fully understood, but it involves the intense magnetic fields and the furious swirling of matter and the spin of the black hole near the horizon, somehow channeling and flinging a fraction of the infalling material outward in tight, powerful beams rather than letting it all fall in. These jets are among the most powerful phenomena in the universe, carrying titanic amounts of energy across vast distances, and they show that a feeding black hole is not just a passive drain, but an active engine, both consuming matter and violently expelling some of it back into the cosmos with tremendous force. Perhaps the most surprising discovery about supermassive black holes is that they are deeply connected to the galaxies that host them, growing up together in a kind of partnership, despite the black hole being tiny compared to the galaxy as a whole. Astronomers found that the mass of a galaxy's central black hole is closely related to the properties of the galaxy around it, a tight connection that was completely unexpected because the black hole, though enormous, is minuscule compared to the whole galaxy, and its direct gravitational reach extends only a tiny fraction of the way across it. This connection suggests that the growth of the black hole and the growth of the galaxy are somehow linked, that they influence and regulate each other as they form, and the leading explanation is that when the central black hole feeds and blazes, the tremendous energy it pours out can heat and blow away the surrounding gas, shutting off both its own feeding and the formation of new stars in the galaxy, a kind of feedback that ties the fate of the giant black hole to the fate of its entire host galaxy. This means that supermassive black holes, far from being mere curiosities lurking at galactic centers, may play a crucial role in shaping the galaxies themselves, regulating how they grow and how many stars they form, so that these giant black holes are woven into the very story of how galaxies, including our own, came to be as they are. The history of the universe's structure, the building of the great galaxies, may be inseparable from the history of the supermassive black holes at their hearts, the two growing and influencing each other across cosmic time in ways we are still working to understand. It is a profound shift in perspective to realize that the supermassive black hole at the center of a galaxy is not just sitting there passively, but may be a key player in the galaxy's whole life story. And it means that understanding these giant black holes is essential to understanding how the universe came to look the way it does. The dark giants at the centers helping to sculpt the luminous galaxies around them, including the Milky Way we call home. We met Hawking's astonishing discovery that black holes are not perfectly black, but slowly leak radiation and evaporate, and we touched on the deep puzzle it created, but that puzzle, known as the information paradox, deserves a fuller treatment because it has become one of the most important unsolved problems in all of physics, a crack to which physicists hope to glimpse the deepest laws of reality. To understand the paradox, you need one crucial principle from quantum mechanics, which is that information is never truly destroyed. In the quantum view, the complete information about any system, every detail of what it is made of and how it is arranged, is always preserved in principle, so that the present state of the universe contains, encoded within it, a perfect record of its past, and nothing is ever utterly erased. This conservation of information is one of the deepest and most cherished principles in physics, woven into the very foundations of quantum theory. Now, consider what happens when something falls into a black hole, and the black hole later evaporates away through Hawking radiation. Whatever fell in, a book, a star, a person, carried an enormous amount of information about itself, all the details of its structure and arrangement. That information vanishes behind the horizon, and then, over the eons, the black hole slowly radiates away and eventually disappears entirely. But here is the problem. Because Hawking's calculation suggested that the radiation coming out is essentially random and featureless, carrying no information about whatever fell in, depending only on the black hole's mass, spin, and charge, and nothing else. So, if the black hole evaporates completely, emitting only this featureless radiation, then the information about everything that fell in would be gone forever, utterly destroyed, which flatly contradicts the principle that information can never be lost. This is the information paradox, a stark conflict between two of our most basic theories: general relativity, which describes the black hole, and quantum mechanics, which insists information must survive, and they cannot both be fully right. This paradox sparked one of the great intellectual battles in modern physics, lasting decades, with brilliant minds taking opposite sides and the matter genuinely unresolved for a very long time. On one side, some argued that the information really is lost, that black holes simply destroy it, even if that means modifying quantum mechanics, while, on the other, many insisted that information must be preserved, that quantum mechanics cannot be violated, and that the information must somehow escape the black hole, perhaps subtly encoded in the radiation, in a way Hawking's original calculation missed. The debate was so famous and so hard fought that Hawking himself made a public bet on the outcome, and years later, in a notable moment, he conceded the bet, coming to believe that the information probably is preserved after all, though exactly how remained unclear, which is itself a wonderful example of a great scientist changing his mind in the face of new arguments. The struggle to resolve the information paradox has driven some of the most profound theoretical physics of recent decades, and it has produced ideas that may point toward the long sought theory of quantum gravity. One of the most important is the holographic principle we explored in the story of the universe. The startling suggestion that all the information about what falls into a black hole might be stored on its two-dimensional horizon like a hologram rather than vanishing into the center, so that the information is not lost but written on the surface and could, in principle, come back out in the radiation. This idea that the three-dimensional contents of a region might be fully encoded on its boundary emerged largely from thinking about black holes and the information paradox, and it has become one of the most influential ideas in theoretical physics, hinting at a deep and unexpected connection between gravity, information, and the nature of space itself. In very recent years, there has been real progress, with new theoretical work suggesting that the information does indeed escape, preserved as the black hole evaporates, and beginning to show, in careful calculations, how the radiation can carry the information out after all, apparently resolving the paradox in favor of quantum mechanics, even if the full picture is still being worked out. What makes all of this so important, beyond the specific puzzle, is that the information paradox sits exactly at the collision point between general relativity and quantum mechanics, the two great theories that we have never managed to fully unite, and black holes are the one place in nature where both must be considered at once, where the immense gravity of relativity meets the quantum behavior of the radiation. This is why so many physicists believe that black holes, and the information paradox in particular, are the key to finding the theory of quantum gravity, the deepest theory of all, that in puzzling over what happens to information in a black hole, we are being led toward the unification of physics itself. The black hole, that simple sounding object from which nothing escapes, has turned out to be perhaps the most profound laboratory in the universe, the place where the deepest laws of reality are being forced to reveal themselves, and where the next great revolution in our understanding may well be born. No discussion of black holes would be complete without addressing the questions that most fire the imagination, the ones about what lies at the very center, whether black holes might be tunnels to other places, and whether their strange mirror images might exist. And here we must be especially careful to separate what physics actually says from the speculation that surrounds these objects in popular culture. Start with the deepest question: what is actually inside a black hole, at the very center? Our current theory, general relativity, gives an answer that is really a confession of ignorance, predicting that at the center lies a singularity, a point where matter is crushed to infinite density and where the curvature of space-time becomes infinite, which is to say, a point where the theory breaks down completely and stops giving sensible answers. A singularity is not really a description of something but a signal that our physics has failed, that we have reached a regime where general relativity can no longer be trusted and where we would need the missing theory of quantum gravity to know what truly happens. So, the honest truth is that we do not know what is at the center of a black hole, that the singularity our equations predict is almost certainly not the real story, but a placeholder for our ignorance, and that the true nature of the black hole's interior is one of the great unknowns, awaiting a deeper theory. It may be that quantum gravity will replace the infinite singularity with something finite and strange, perhaps an exotic state of matter, perhaps something we cannot yet imagine, and some speculative ideas even suggest that the interiors of black holes might connect to new regions of space-time or give birth to new universes, though these remain firmly in the realm of unconfirmed speculation. What we can say with confidence is that the inside of a black hole beyond the horizon is hidden from us forever, since no information can escape to tell us what is there, and that our theories, as they stand, cannot describe its heart, which is a profound and humbling limit on our knowledge. Then there is the famous idea of the wormhole, the tunnel through space-time that might connect distant regions of the universe, or even different universes, beloved of science fiction as a shortcut across the cosmos. This idea is not pure fantasy, because the equations of general relativity do allow, mathematically, for such tunnels, often called bridges, which emerge naturally from the mathematics of black holes and were studied by Einstein himself. But there are enormous problems with the notion of actually traveling through one, because these tunnels, as the basic theory describes them, would be deadly, unstable, pinching off and collapsing far too quickly for anything to pass through, and keeping one open would require some exotic kind of matter with strange properties that may not exist in nature at all. So while wormholes are a genuine feature of the mathematics and a fascinating area of theoretical study, there is no evidence that traversable ones exist, and the dream of using them to travel across the galaxy or between universes remains, for now, firmly in the realm of speculation rather than established science. Related to the black hole is its strange theoretical mirror image, the white hole, which would be a black hole running backward in time, a region that nothing could enter, and from which matter and light could only emerge, spewing out rather than swallowing. White holes arise naturally in the mathematics of general relativity as the time-reversed counterparts of black holes. But unlike black holes, there is no known way for a white hole to actually form in nature, and they would be wildly unstable and seem to violate the ordinary flow of cause and effect. So most physicists consider them mathematical curiosities rather than real objects that exist in the universe. They are a wonderful illustration of how the equations of physics sometimes permit possibilities that nature does not appear to use, solutions that are valid on paper but that seem to have no counterpart in the real cosmos. And they remind us to be careful, to distinguish what the mathematics allows from what actually exists. The lesson running through all of this is the importance of separating the firmly established from the speculative, because black holes attract more wild speculation than almost any object in science, much of it presented as though it were settled fact. What is firmly established is remarkable enough: that black holes are real, that they trap everything, including light, that they warp time and space dramatically, that they radiate and slowly evaporate, and that they pose deep puzzles about information and the core nature of reality. What remains genuinely unknown and speculative is what lies at their centers, whether wormholes could ever be traversed, whether their interiors connect to anywhere else, and what a complete theory of their nature will ultimately reveal. The line between these, between the well-tested science and the imaginative speculation, is exactly where good physics lives, and black holes, sitting right at the frontier of the known, are a perfect place to practice the discipline of being amazed by what we have actually discovered, while remaining honest about the vast amount we still do not understand, holding wonder and rigor together as we contemplate the strangest objects in the universe. There is one more kind of black hole worth discussing, a hypothetical sort that may or may not exist, but that connects to some of the deepest mysteries in the universe. And these are the primordial black holes. Black holes that might have formed not from dying stars, but in the chaos of the very early universe itself. Recall that the early universe, just after the Big Bang, was incredibly hot, dense, and slightly uneven, with tiny variations in density from place to place. The idea is that in the densest spots, the matter might have been packed so tightly that it collapsed directly into black holes, right there in the first instance, without ever forming stars first. Unlike the black holes born from stars, which must be at least a few times the mass of the Sun, these primordial black holes could, in principle, have come in almost any size, from tiny ones no heavier than a mountain to large ones, depending on the conditions when they formed, and they would be ancient relics of the universe's very first moments. Whether primordial black holes actually exist is genuinely unknown, but the possibility has become very exciting because of a tantalizing connection to one of the great mysteries we explored in the story of the universe, the puzzle of dark matter. Remember that most of the matter in the universe is some invisible substance we cannot identify, detectable only by its gravity. And remember that the leading candidate, some new kind of particle, has stubbornly failed to show up in experiments. This has led some physicists to revisit an intriguing alternative, the idea that dark matter might not be an exotic new particle at all, but might be made of primordial black holes, vast numbers of them left over from the early universe, dark and invisible by their very nature, betraying themselves only through gravity, which is exactly what dark matter does. It is a genuinely appealing idea that the mysterious dark matter might be nothing more exotic than black holes formed in the first instance of creation. This possibility has been intensely investigated, and while it has not been ruled out entirely, it faces serious constraints, because black holes, even dark ones, would reveal themselves in various ways if they were common enough to make up all the dark matter. They would occasionally pass in front of distant stars and briefly brighten them through their gravity, an effect astronomers have searched for, and they would affect the early universe and the cosmic structures in detectable ways. And these searches have largely ruled out primordial black holes as the dark matter across most ranges of possible sizes. There remain, however, a few windows of possible mass where primordial black holes have not been excluded and could still, in principle, account for some or even all of the dark matter. So the idea remains alive, if constrained, and the recent detections of black holes through gravitational waves have revived interest in whether some of them might be primordial rather than born from stars. The smallest primordial black holes connect to Hawking's evaporation in a dramatic way, because while a black hole formed from a star evaporates so slowly that it will outlast the stars themselves. A sufficiently tiny black hole of the right small mass would evaporate much faster, and some primordial black holes of just the right size would be reaching the end of their lives and evaporating right now in the present day universe. Such a black hole would end its life in a final burst of high energy radiation as it evaporated away completely, and astronomers have searched for these telltale flashes, which would be a spectacular confirmation both of Hawking radiation and of the existence of primordial black holes. So far, no such flash has been definitively seen, which places further limits on how many tiny primordial black holes there can be. But the search continues, and detecting one would be a monumental discovery. The first direct observation of Hawking's predicted evaporation and proof that black holes can be born from the early universe. All of this points to how alive and unfinished the science of black holes remains, full of open questions and on the verge, perhaps, of major discoveries. We have moved, in just a few decades, from doubting whether black holes were real at all to detecting them by the dozens through gravitational waves, photographing their silhouettes, weighing the giants at galactic centers, and seriously investigating whether they might solve the mystery of dark matter or reveal the secrets of quantum gravity. The coming years promise even more, with new gravitational wave detectors planned, including ambitious ones to be placed in space that could sense the mergers of the supermassive giants, with improved telescopes that will sharpen our images of black hole shadows, and with ongoing searches for the evaporating flashes of primordial black holes, and for clues to the information paradox. The black hole, which began as a strange prediction that even Einstein doubted, has become one of the richest and most active frontiers in all of science, a place where the largest questions about the cosmos and the deepest questions about the laws of physics come together, and where, in all likelihood, some of the great discoveries of the coming decades are waiting to be made, hidden in the darkness, ready to teach us things about the universe that we cannot yet even imagine. It is worth following the full life story of a black hole, from birth to ultimate death, because black holes are not eternal and unchanging, as they might seem, but have their own long biography of formation, growth, and, astonishingly, eventual demise. Most black holes are born, as we have seen, in the death throes of massive stars, when a giant star exhausts its fuel and its core collapses, leaving behind a stellar black hole. But their story does not end at birth. Over time, a black hole can grow, feeding on any gas, dust, stars, or other material that strays too close, adding their mass to its own. And black holes can also merge with one another, as we now regularly observe through gravitational waves, two black holes spiraling together and combining into a single, larger one. Through feeding and merging, black holes can grow from the modest size of a dead star up toward the supermassive giants at the centers of galaxies, building themselves up over billions of years. Our detection of black hole mergers through gravitational waves has, in just the last decade, transformed black holes from objects we could study only one or two at a time into a whole population we can survey, because each merger sends out its distinctive ripple, and we have now detected many such events, building up a growing census of the black holes in the universe. This has revealed black holes of sizes we had not clearly seen before, and is teaching us how common they are, how they pair up, and how they merge, turning the study of black holes into a genuine statistical science. There is also an interesting puzzle about a missing middle, because we readily find stellar black holes a few times the mass of the Sun, and supermassive ones millions or billions of times heavier. But the intermediate ones in between have been harder to find, and tracking down these intermediate mass black holes, the presumed stepping stones between the small and the giant, is an active area of search. The most astonishing chapter in a black hole's life story is its death, because, thanks to Hawking's discovery, we know that black holes are not truly permanent, but very, very slowly evaporate, leaking away their mass as faint radiation over spans of time that defy comprehension. This evaporation is fantastically slow for any normal black hole, so slow that a black hole formed from a dead star would take something like a number with 67 zeros in years to evaporate completely, almost unimaginably longer than the current age of the universe. And the supermassive ones would take vastly longer still. So, on any timescale that matters to us, black holes are effectively permanent, growing rather than shrinking in the present universe, where they can still feed on surrounding material faster than they evaporate. But in the deep future, after the stars have all died and the gas has run out, and there is nothing left for them to feed on, the black holes will finally begin, ever so slowly, to lose the race, radiating away faster than they gain. Strangely, a black hole evaporates faster as it gets smaller, radiating more intensely as it shrinks, so that its final moments, after eons of imperceptible fading, would come relatively quickly, ending in a final burst of radiation as the last of it disappears. This means that in the far future of the universe, the era we discussed in the story of the cosmos, when only black holes remain, those black holes will, one by one, over almost endless stretches of time, evaporate away, the smallest first and the largest last, each ending its unimaginably long life in a final flicker, until, at last, even the most massive black holes are gone, and the universe is left without them. The black holes, which will outlast the stars, the galaxies, and ordinary matter itself, becoming the last great structures in the cosmos, will themselves eventually fade, marking the end of the black hole era and the universe's descent into its final, featureless darkness. There is something profound in this, that even black holes, those seemingly eternal pits of no return, the most extreme and permanent seeming objects in all of nature, are ultimately temporary, born from dying stars, growing through eons of feeding and merging, and finally, over spans of time that dwarf the entire history of the universe so far, evaporating away into nothing. The black hole's life story stretched across timescales so vast they can only be written as numbers with dozens of zeros, is, in a sense, the longest story there is, the slowest and most patient process in the cosmos, and it ends, like everything else, in dissolution. In learning that black holes are born, grow, and die, we have come to understand that nothing in the universe is truly eternal, that even the darkest and most powerful objects there are will one day fade, and that the whole grand cosmic story, from the brilliant birth of stars to the final evaporation of the last black hole, is a tale with a beginning, a long middle, and an end. The black hole, which began this story as a place from which nothing escapes, ends it as a reminder that, given enough time, everything escapes in the end, even the substance of a black hole itself, radiated away into the dark. What makes black holes so endlessly fascinating in the end is that they sit precisely at the breaking point of our understanding, the place where the rules we know stop working and something deeper, something we have not yet grasped, must take over. They are where Einstein's beautiful theory of gravity meets its limits, where the very large and the very small are forced together and refuse to agree, where infinities appear that signal the edge of human knowledge. Every black hole is, in a sense, a piece of the unknown sealed inside an event horizon, a fragment of mystery embedded in the universe, and the effort to understand them is really the effort to push the boundary of physics itself into new territory. They are not just objects to be catalogued, but signposts pointing toward the deeper laws of nature that we have not yet discovered, and there is a real wonder in how far we have come. Consider that black holes were, for most of their history, regarded as little more than mathematical curiosities, objects that the equations reluctantly allowed, but that surely could not really exist, dismissed even by Einstein himself. And now we know that the universe is full of them. That one sits at the heart of nearly every galaxy, including our own, that they collide and send ripples across space-time that we can detect on Earth, and that we have taken their picture. We have reasoned our way from a clergyman's speculation through the warped geometry of general relativity to the quantum glow at the edge of the horizon, to direct images of the dark shadows themselves, all in the span of a couple of centuries. It is one of the great triumphs of the human mind, this gradual mapping of the most extreme and most hidden objects in existence. So, the next time you consider a black hole, remember that you are contemplating the strangest place in the universe and, in a way, the most honest, because a black hole is where nature itself admits that our current understanding runs out, where it hangs a sign that says, "Here be mysteries we have not yet solved." They are at once the simplest objects in the cosmos, described by a mere handful of numbers, and the deepest, holding within them paradoxes that may take a revolution in physics to resolve. They are the death of stars and the hearts of galaxies, the testing ground of our greatest theories, and the final monuments of the cosmic age. And they remind us, perhaps more than anything else in the universe, of how much there still is to learn that even now, after everything, the cosmos holds places where the rules break down and the answers wait, sealed behind the horizon for minds bold enough and patient enough to find them. The black hole is the universe's great unanswered question, and the fact that we can ask it at all, that small creatures on a small planet can photograph the shadow of the unknown and reason about what lies within, is itself one of the most remarkable things in all of science.